Hi there everyone, it's DB2 time again. And this is chapter 8 about predicate evaluation. So predicates are expressions, and we have just talked about expression evaluation in chapter 7. But I think predicates deserve a special mention and special attention in the context of database systems. Predicates are all around. Predicates are being used to filter, to cut down high data volumes. The efficient evaluation of predicates is instrumental for good performance of relational database systems. And as we will find, there is some clever technology built into these systems to evaluate these predicates efficiently and to have very efficient filtering facilities inside these systems. Let's have a closer look. All right, chapter 8, predicate evaluation. Of course, we will formulate a particular probe query for that. It's probe query Q7 already. Okay, and one of its prominent features, of course, will be the where clause. This is one of the syntactic constructs in SQL that allows for the specification of filtering predicates. And here is one such predicate. As you can see, it could be a conjunctive or disjunctive predicate. It could be even more complex. It could consist of many sub-expressions, Boolean sub-expressions that we connect together using the Boolean connectives and, or, and not. There are even more connectives implemented in the SQL standard. So it's all about these Boolean expressions down here. And as the text of the slide says, of course, they can occur in the where clauses, but there's also the having clauses and the filter clauses that might not be as commonly used, but they can be used to cut down the volume of data that streams into aggregate operations in SQL. Okay, so what do we expect from Q7 here? Of course, we expect it to scan all the rows in the ternary table in this example. All right, all the rows will be bound to variable t. Once t is bound, we will evaluate this Boolean expression down here. And as it's using Boolean connectives like the and or alternatively the or, we would hope that the system cleverly exploits tricks like the Boolean shortcut, which will allow the system to maybe only evaluate parts of an expensive predicate. Okay, what we assume here in the following minutes is that this particular predicate is not supported by specific index data structure. Index data structures are implemented in relational database systems to do many things, but of course the primary concern is the efficient evaluation of predicates, maybe predicates like the one you're seeing on the slide right now. But let's not talk about indexes or indexes yet. This is a super important core topic of the DB2 course, and it deserves its special chapters, and we will of course do that very soon. But this is about the Boolean expressions themselves, the filtering themselves. Okay. So when we throw our database X-ray on Q7, our explain analyze, for example, then we would of course see the plan that is being used to evaluate Q7. And this is just a Q7 using the and keyword, so that would be the conjunctive version of the filtering predicate that we have just seen. As before, we are assuming a ternary instance of 1000 rows. Of course, this will work for any ternary table, and indeed it makes a difference whether we are filtering very small tables or very large tables. This will lead to different amounts of effort that we have to invest in predicate evaluation. As you can imagine, if this would be a ternary table of 1,000,000 rows, then every bit, every millisecond rather, that we can save in efficient predicate evaluation would add up to substantial savings. All right. So let's have a look at the query plan, and as you can see, it's a one operator query plan. So we are just using the sequential scan over ternary to access all the rows T and also filter the rows. So the sequential scan has built-in filtering capability. whenever a predicate cannot be evaluated by a specific index data structure, then we can fall back on sequential scan. With its built-in filtering facility, it can evaluate predicates that are not supported by an index, as in our sample queries right now. Okay, you see that we have indeed used an explain analyze here. So the query has indeed been performed and executed. Before the query was executed, we saw that PostgreSQL has made a good guess, or a bad guess, an estimate of how many rows will qualify regarding the predicate, how many resulting rows we will see when we evaluate this query. And you see the best guess that PostgreSQL had at this particular point in time was 1 row will be returned. When the query was actually executed, we then saw that 4 rows had been returned. So the estimate was a bit off. It's not too bad in this particular case. We will see bad estimates by PostgreSQL, and we will see very clever and good ones. But, well, PostgreSQL is off at this particular point, and we will later understand why it had to be off. All right. Okay, so then we see the filtering predicate, the Boolean expression itself embedded into the plan, and you can see that some explicit casting has been applied and that some explicit parentheses have been introduced. Okay, we will see many more of such query rewrites, such predicate rewrites rather, in the upcoming minutes. Okay. And then, of course, if only 4 rows of 1000 rows in table ternary could qualify and are seen in the actual result of the sequential scan, then, of course, 996 rows have been removed by this filtering process, by the predicate process. Okay. So, filter predicates can be evaluated by the sequential scan, in particular if they are not supported by an index. And the system already tries to make guesses of how many rows will pass such a filtering predicate and will be seen in the result. So that was the guess. That's the actual value of, or the actual number of rows that we have seen. This value, this 1000th, or this value are called the selectivity of the predicate. How many rows will be able to pass 1 of 1000, or the actual selectivity of the predicate has been 4 of 1000. So very selective predicate. Almost all of the rows couldn't qualify. Only a single, or actually 4 of 1000 rows could qualify. This predicate would be termed a very selective, very picky predicate. Okay, of course, the higher the selectivity value, the less selective is the predicate. All right, so a predicate that just reads true would be still a valid predicate, but it wouldn't be selective at all. Any row could pass whatsoever. And the selectivity value of such a predicate would be 1000 divided by 1000, or 1. That's the maximum selectivity. Such a predicate is not used, or cannot be used, to really cut down data volume. All right, so let's switch over to the editor again. And as you can see, I brought my ternary table with me, as always. And it has been populated with 1000 rows indeed. Okay, so this would be the explain verbose invocation on our query Q7, our probe query Q7, featuring the conjunctive version of the predicate. So let's see whether we can see what we've just observed on the slide. That would be the query plan without the analyze data. So the query has not been performed yet. It's just about query planning and estimates. You see the predicate itself embedded into the filter field here of the sequential scan, and our guess at this particular point in time that only 1 row will qualify. We know that the system is off there. So, and we could see that if we try the analyze here. Okay, now the plan wraps around. I'm sorry for that. Can we still read it? I think we can. This is the old estimate that we had. 1 row qualifies. Indeed, 4 rows qualified, and 996 were removed. This is a rather selective predicate. We could of course change the predicate and thus influence its selectivity. All right. So we could make the predicate less selective, less picky. So any C value in row T that is less than 2 would be okay and would qualify regarding this change predicate now. Okay. So we expect more rows to qualify and less rows to be removed by the filter now. Let's see. Oh yeah, indeed. The estimate is still 1. It's now really off from the real value of rows, or the real number of rows that we've seen in the result. It's 49 rows. 951 have been removed by the filter. So less rows have been removed. The predicate is less selective. Okay. So as I said in the very beginning of the video, this is just about expression evaluation in a sense. Predicates are Boolean expressions. And as you might have imagined, the expression interpretation, the expression evaluation infrastructure that is present in PostgreSQL anyway is being used to evaluate filter predicates that have no particular special index support. So indeed, if we are faced with such a predicate expression here, and it's not supported by indexes, we would just invoke the expression interpreter inside PostgreSQL. Sequential scan would invoke the expression interpreter inside PostgreSQL to evaluate this particular Boolean expression. And of course, we will see a familiar setup. We will see a linearized program evaluated top to bottom that would have been generated from this particular Boolean expression. Again, using a post-order traversal of the expression tree, of the abstract syntax tree of this specified predicate. Okay, so let's see what's going on here. We would first prepare the extraction of the fields A and C from row T. Okay, so A and C. Indeed, these are the two fields involved in this predicate. The scan fetch sum makes sense, and later on in the program we indeed find accesses to field C and accesses to field A at these points. Makes sense. All right. Okay, so evaluating from top to bottom, we would just extract field C and then perform the less than comparison with the literal 1. All right, this already delivers a Boolean value. And you can see that Boolean value would be placed in the argument slot of the bool and step first operator of our interpreter. Okay, bool and step first indeed implements the Boolean shortcut we were hoping for. Bool and step first is aware of the fact that if the value that's coming in here is false, then there is no chance for the entire conjunction, for the entire AND expression to ever yield true again. So we might as well just stop predicate evaluation at this particular point. The outcome will be false for sure. Okay, see the comment here on the right hand side. If this is detected, indeed the bool and step first will make use of the fact that our expression interpreter supports jumping, and it will perform this jump that I've indicated here on the side to just shortcut the entire rest of the evaluation here and immediately indicate that the outcome of this predicate will be false. All right. If this has been true, then of course we need to consider the rest of the predicate. So we would access field A, we would perform the modulo operation with the literal 2 at this particular point, and then compare the outcome of the modulo with the literal 0. And here again, at this particular point, we will find the next Boolean value of the next sub-predicate, the sub-expression, TA modulo 2 equals 0. Okay, this would be the last sub-predicate that goes into this particular conjunction. And well, the bool and step last opcode of our interpreter would perform the necessary logic here, would check if this particular value is true and we have reached this, this instruction, then the entire predicate will be true. Okay, So this is a linearized expression interpreter program used to evaluate predicates that receive no index support. Okay, so for one brief second, let's switch over to the PostgreSQL source and see whether we can find what we have just discussed here. So let me check. So here I am in the expression interpreter of PostgreSQL again. And as we know, it's relevant also for the evaluation of predicates without index support. Okay, and as you may recall, this is the implementation of the individual opcodes of our interpreter. We have seen that before when we were talking about the evaluation of arithmetic expressions in chapter 7. And if you scroll down far enough, then you will find, let's close the window at the bottom, then you will find indeed implementations of the bool and step first, and then also the bool and step last opcodes. All of them together implement the logic that is used to implement conjunctive predicates. Some comments here in typical awesome PostgreSQL style that inform you about the behavior of predicates when nulls are involved or whether Boolean shortcut is possible. So let's see what's happening here. So the bool and step first is not doing much. It's actually only setting a flag that we have not just seen any null value in any of the subpredicates of our conjunction. Okay, so we keep a protocol of that because the early presence of a null value may yield an early null also in the evaluation of such a predicate. So we've just initialized this, then we fall through to the bool and step. So the control flow of C just brings us into this particular part. Okay, and let's ignore the null handling for a minute. What you can see here is a check. The check of the Boolean value of the argument slot. The Boolean value of the argument slot is being inspected. If that Boolean value should turn out to be false, all right, please note the Boolean negation here in C. If this Boolean value turns out to be false, then we immediately perform a jump. We will perform a jump to jump done. We know that the entire predicate will yield false, and we will shortcut the rest of the evaluation of the residual predicate, saving time, saving precious milliseconds that will add up when we evaluate this predicate millions of times possibly. Okay, I invite you to actually read the logic that is behind these bool and of course also the bool or step opcodes, just to understand how the handling of null is being performed and how Boolean shortcut is taken advantage of. It's really instructive and nice to see. If we look at the implementation of the sequential scan operator, which is found in another file, it's found in the exec scan file. I've just switched over to that file, and you can see this is the exec scan implementation of PostgreSQL. The sequential scan is implemented here. Then we should be able to scroll down here and at some point find the invocation of the expression interpreter for filtering predicates. So let's see, let's not consider all these details here. So they are talking about the qualifier already. That would be the Boolean expression, the filtering expression that is placed in the filter field of the sequential scan. And if we look a bit further, then we see that indeed the sequential scanning is starting here. So the next row is being read from the heap file. All right, let's more stuff. All right, okay. So if there is indeed a qualifier, so if there is indeed a filtering field in our sequential scan, then it makes sense to invoke the expression interpreter, the exec qualifier, a different word for predicate, the exec qual routine, which will indeed use the predicate, the filtering predicate of the sequential scan at the current context determined by the current row to find the Boolean value, the Boolean value of the outcome of the predicate for this particular row. If this should turn out true, then indeed we will perform further computation for this particular row. If this should turn out false, everything here is skipped. The row is just discarded. Okay, so much for now. There is much more to be said. Also, in the case of PostgreSQL, when it comes to the efficient evaluation of predicates, it will also be super interesting when it comes to MonadDB, because it will open up a nice window inside the CPUs and their behavior. But let's not jump ahead. In the next video, we'll dive deeper into the predicate evaluation in PostgreSQL. See you then.